first bit. You can read the first bit about rational functions, have defining equations that contain rational expressions. The equation of a rational function can be expressed in the form f of x equals p of x over q of x, where p of x and q of x are polynomial functions and q of x cannot be equal to 0. So which of the following are rational functions? If you determined a, c, and e, then you are correct. Congratulations. Okay. Why is b not a rational function? Okay, this is exponential, right? Why is d not a rational function? Absolute value. Okay. So, and these guys are the graph of the basic rational function. So we're going to start out with something. Let's see what this looks like. The expression y equals 1 over x is not defined for which values of x? 0. Complete the following table of values for the function y equals 1 over x and use it to sketch the graph of y equals 1 over x. Okay, so you can do that. I can pause this. So here's the table filled in, and you can look at that, and now we're going to graph this. So I'm going to repause. Okay, so we've got the points down. What do we do with these points now?
Yeah, it's one graph.
So we what do I need? Arrows. Okay. What do I do to this graph? Same thing. Okay, so there's the graph y equals 1 over x. Right? Now we could graph that on a graphing calculator as well. I mean, so it's nicer to see it on a nice grid, right? So let's use this graph to answer the following questions. Is the graph continuous? No. Why not?
Because x indefinitely approaches 0, but it actually never crosses 0.
So, sorry, what was that again?
Why?
Undefined when x equals 0? How close to 0 can we get? Infinitely close. You're as close as you want, but you can't get to 0. Are there any relative or absolute maximums or minimums?
Yeah. Oh, no.
No. Explain.
Just an equal graph.
Okay, so no parabolic shape. And say you can get as large or as small as you want. Are there any zeros? No, why not? There's no value of x that will give us a y value of 0? Is there a y-intercept? Why? Undefined when x equals 0? Let's clean that up a bit. So undefined. Describe the symmetry.
Symmetrical x axis. What? Oh wait, no, yeah. Sorry, it's the symmetrical. This line reflective on line.
reflected on the line y equals negative x. So if we graph this line, then we can see that that's a reflection. What happens to the y values as the x values approach 0 from the positive side? They get really, really large? What do you want to say?
Yeah, they get infinite. It never touches.
They get infinitely large.
Oh, the
Sure.
one point two.
Infinitely. Didn't spell that right. And what else about them? So they get infinitely large, and
We also get infinitely small.
no.
Well,
Well, so it's asking about it as approaches from the positive side and the negative side, and you're just going to say they get infinitely large when we talk about the negative side, right? So how are you going to distinguish? Okay, so they get infinitely large and are positive. And here, they get infinitely large. And are negative. Graph has one vertical asymptote. A vertical asymptote is a vertical line the graph gets closer and closer to but never touches. What is the equation of the vertical asymptote? X equals 0. So you can get as close to x equals 0 as you want, but you can't make x 0. What happens to the y values as the x values approach negative infinity? Okay. They get infinitely small. And what else? And are negative. And answer the next one.
Same thing.
Same thing, only they're positive. So we can get y values as large as we want. We can get y values as small as we want, but we cannot get a y value of 0. If the y values get closer and closer to a particular value, as the x values get very large, think big, really big, either positive or negative, then the graph will have a horizontal asymptote at that particular value that y approaches. What is the equation of the horizontal asymptote for the graph?
Y is equal to 0.
Y is equal to 0. Right? So we can get really close to the line y equals 0, but we can never make y 0, right? We can get as close to it as we want, but we can't make y 0. Now, when we're talking about horizontal asymptotes, we're talking about lines as we go to infinity, right? I mean, you may cross an asymptote close in, but it's what happens. So, you know, you might have a curve that sort of comes up above and then goes below and stays infinitely close, something like that. That's fine. You can cross it. But what we're talking about when we're talking horizontal asymptote is the values as we tend to infinity, both positive and negative. Remember, the domain is a set of all possible values of the independent variable. What values of x are not allowed for y equals 1 over x? So x equals 0 is not allowed. What is the domain of y equals 1 over x?
X not X not equals 0.
Yeah, let's just keep it easy, right?
X small.
Set of all x such that x cannot be 0. Remember that the range is a set of all possible values of the dependent variable. What values of y will never occur? y equals 0, and what is the range?
Y.
Set of all y such that y cannot equal 0. Okay, how are we doing? Any questions?
No, would it still be correct if you put y is less than 0, less than y?
No, because it's just 0 that equals.
You'd have to write it in two parts. Y is less than 0, comma, y is greater than 0. It would be correct, but awkward. Use the graphing calculator to analyze rational functions. Before graphing rational functions in your calculator, set the window to negative 9.4 to 9.4 by 1s, and negative 3 to 4 by 1s.
Oh, wait, no, I did it. No, I did it.
So, okay, what were we setting it to? Negative 9.4 to 9.4 by 1s. And what was the other one? Negative 3 to 4 or something? Negative 3 to 4, also by 1s? Okay. Now, the reason we call this, or it's called the friendly window sometimes, and basically what it does is it's the number of pixels that are on the screen fit with that 18.8, right? It's some multiple of 18.8, the number of pixels, right? So that you won't get stuff happening that we don't want to happen here, which I'll show you. Okay, so we want to graph y equals x plus 3 over x plus 1, x minus 2 on your graphing calculator, and sketch the graph in the table below, labeling all of the important points. Also determine the following information. Okay, so let's just start off by graphing it.
We get different. Okay, that's right.
X plus 3 divided by bracket.
Why does this? How do you not read it? Why? No, you didn't.
It's because if it goes straight
Well,
up
I
there,
remember. Oh, really?
Graph.
Yeah.
What did you get?
Okay, so is that what we got? Yes, no?
That's stupid. I think.
Yeah? Here's what happens if you use the standard window.
You can't. Oh.
Actually, nothing. So
What is
nothing exciting. Yeah, I know. So now that may be a function of the calculator. So let me try the TI-83.
What if they're both what happens if they all blow up? What if this looks very inappropriate?
I told you. It's graph already. If the line goes straight, basically.
Yeah.
All right, what was it? X plus 3.
That's like six.
X plus 1.
X minus 2.
X minus 2.
Wait, is it going to the left then?
Oh.
Okay, so this is something that's been cleaned up on the 84 that still exists as an artifact on the TI-83, I guess. Right?
Woohoo! No, I think it's 'cause
So if you're using an 83, and what it is, it's trying to join the point, right? It knows, we know this is infinitely large here, and this is infinitely small, and because of the window setting on this one, if I change the window to the negative 9.4, we'll see those disappear. Because of the window, it's just trying to join this point to that point.
It's a heartbeat monitor.
Okay, so if I do change this to negative 9.4 to 9.4, and I should be able to leave the others the same, then that artifact thing disappears, right? Okay, so a lot depends on the calculator you're using. If you're using an 84 plus and it's got the newer firmware, you're not going to have that problem. Okay, but just be aware if you see something that looks like it's drawing the asymptote, basically I kind of just think of it as drawing the asymptote in for us. You know, but really it's just the calculator is saying I've got a point here and I got a point here and I've got to draw them. So, and this is avoided here because of the friendly window. Okay, anyway, so we're supposed to sketch that, right? And actually, you know, oh, that wasn't fired up yet. I kind of. Go to here. I kind of prefer, I like doing this stuff in Desmos.
Oh, cheating like fake.
thought I liked doing this, and oh, here we go. Y equals.
Oh. Suppose like this goes down.
What was it? X plus 1, x minus 2?
Yeah.
Okay. So we get a nice graph there. We can also see intercepts and stuff, right? You know. And we can get coordinates of those. You know, and so just be aware that obviously if you're doing anything on a quiz, test, final exam, diploma exam, whatever, you have to use the handheld. But if you're working at home or something, you want to be able to see things a little better, right, with nice scale on and a little grid and everything else, that this works for that as well, right? So you may want to do both, have both available, work within them. Anyways, what did it look like? So we got da-da, and da-da, and in between da-da. I had short-term memory. Oh, okay. So
There was no burger last yesterday. There was the new burger last yesterday. You taste it. They do every Monday. They didn't do it yesterday.
Yeah, I know, right?
okay, so there's our sketch, right? So what is the domain of this?
X
Such that
X equals. Oh wait, and does not.
2.
Oh right. I see.
so we have two restrictions, right? That x can't be negative 1 or 2. Those are the restrictions or non-permissible values, right? Because they would give you a 0 in the denominator, and we can't do that. What's the range? Well, I seem to think the range is like,
Oh, it's 2.
it's not there, and that this actually does go below and above.
It does go below.
It goes, well, it looks like it goes.
It looks radical.
So what do we have to find?
The lowest point then.
Relative minimum.
Yeah, it goes
Relative
below.
max.
Relative.
The vertex of that thing.
Over 18. Negative 1 away.
Relative
We need
points.
to zoom out a bit to see what's going on.
It's just going to go like that forever. It's not helpful.
Okay.
But that means it's just a straight line.
So
If you zoom out,
what are we looking for? What points?
The vertex of that.
Okay, so we're looking for the relative maximum here. What else?
relative minimum is there.
Relative minimum here, which I think might be there. Kind of, it's showing a dot there, so I'm thinking maybe that's a point of important.
I don't know how that's important, but okay.
It's like negative 3 or 4.
So we have a number of points that are of interest. So that I believe is the that's the y-intercept. Let's get rid of that. That's the relative maximum, right? But we need to do this obviously on our calculators, right?
Yeah, I got that.
Yeah.
Okay, so graph.
I'm so good at this.
Let me change this window because we were at negative 3 to 4, right? Because we want to, we would need to be closer in on this. So, I mean, the thing, because, here we can see that it does that, right? It's a lot harder here to see that this thing actually has a minimum point somewhere, right? That it comes down, has a minimum, and then goes back up. So we'll move in a little closer on it. We'll play with the window a bit and stuff. So let's start by finding the relative maximum there. So we want a maximum. Okay, and so we got left bound, and we go around, and we get, ooh, surprise, 0.162. That's the x value. What are we interested in, x or y?
Wow.
We're interested in the y value, so negative 1.48.
We're interested in both. We have to write it down anyways. Wait. If it never touches this point, negative 1 right here, right? It's just straight up.
distance between here and the next unit.
So we'll write this as y is less than or equal to negative 1.48 to handle this part of the graph. We'll write it as y is greater than or equal to whatever to handle this part of the graph. Okay, so how do we find that and what are we looking for? We're looking for minimum in this branch, right? Okay, so we know it's over here somewhere, right? We actually know where it is, but that was because we used the other thing. So, you know, we're looking in the table help us. So, say, well, there's an error there. So we got 0.25. It goes negative. Seems to go to negative 0.75, right around negative 6, and then it's climbing back up again. So then we should be able to figure out our minimum is going to be somewhere in this region, right, in the negative 6 area, okay, using the table. So let's go back to the graph, second calc, minimum, left bound. So now I want to move over to the left of negative 6.
You should really stop doing that.
And then to the right. So I'm just going to go up there where it's obviously larger. And then I want to guess, and I want that to be somewhere in the negative 6 range. And what are we interested in, the x or the y? The y, okay, and let's say we go 2 decimals, so negative 0.08. Okay, so y values are either less than or equal to the maximum of this, which was negative 1.48, and, okay, obviously a poor sketch. If I can move the axis a little. There. Because it did actually drop down below this. That still is a horizontal asymptote because as we go to infinity, the values will come back up towards 0. Right? I mean, they went down as low as negative 0.075 or negative 0.08, but then came up. X-intercepts. How do we find x-intercepts? So I like to go y equals 0 and just find the intersection. Right, you can also do the zeros. So second, how many are there? Okay, yeah. And where is it? It's going to be over here somewhere. Well, actually it's going to be right there, but negative 3, 0. So what am I going to write here under x-intercepts? Negative 3, just the number negative 3, right? Because the intercepts are numbers. It's the value of x where the curve crosses the x-axis. Y-intercept. What do we do to get the y-intercept?
Second calc.
Yeah, second calc, and what do we put in?
Negative 0.
Negative 0? Really? Positive 0 is not good enough for you? And what's the y-intercept? Let's call it negative 3/2. Although if you wrote negative 1.5, I wouldn't object. It's exact, right? So maximum values. So I guess we could say there's a relative maximum, right? I'm not really entirely sure what they want. I don't have the answer. Hang on, let me find the answer sheet. It's asking for maximum value. Is there an absolute max? No. Okay, so let's say that. No absolute maximum. And then let's say there is a relative maximum. Now, the question I was asking was, do we put the coordinates of that point or just the value? So, you know, seeing as we didn't ask for the point, we're just going to put the value. So there's a relative maximum at, and what was it? Negative 1.48, right? Now, I think you should still be aware of where that is. So, you know, I would probably just write down the coordinate on the graph. I maybe would put down the coordinate of the relative maximum. Okay? Or be able to see it, right? So here on this graph, I have the coordinate of the relative maximum. Okay, but we're just talking about the y value, but I, you know, sort of want to know where it is. And then, which one's notebook? Okay, and are there any other relative maximum? No. Okay, minimum values.
There's no absolute minimum.
No absolute minimum.
But there's a relative min.
Yeah, so relative min, negative 0.08. Okay, again, be aware of where that is just in case you need to give the coordinates of it. But if we're asking for the value, the relative maximum value is just that number, and the relative minimum value is just that number. Equations of any asymptotes. So where are their asymptotes?
Right there and right there.
Right there. Okay, so x equals negative 1, x equals 2. What else? That's not it.
It's not it. Is it?
No. Where else? Y equals 0.
Because asymptotes are.
How is it not? Remember, where is the asymptote? When we're looking at horizontal asymptote, where are we looking? Close to 0? No, we're looking at negative infinity and positive infinity. What happens as the values get infinitely large? Positively. What happens as the values get infinitely large? Negatively, we tend to 0, right? The function is tending to 0. So that is a horizontal. So we have 2 vertical, 1 horizontal.
Like it crosses 0.
Yes, it crosses 0. Congratulations. And if we rewind this tape and go back to when I first talked about horizontal asymptotes, what will I be saying?
Infinity.
It's at infinity. It can cross the axis here, close in. We're interested in what happens at infinity. If you don't believe me, go watch the thing later on tonight. Okay? What I specifically said is sometimes they cross.
It doesn't exist.
Right? So maybe what I want to do is I'm going to clean this up and let's do a nice
You can cross it a million times.
cleaner sketch.
Let's
You can cross it a million times.
Okay, so this, right, and has an asymptote at x equals 2. And this has an asymptote at x equals negative 1. And the curve does this. Okay, that we have a relative minimum here at, and what was it, negative 6.16, negative 0.08. And here we've got something that looks like this. We have a y-intercept at negative 1.5. We have this relative maximum, which occurs at 0.16, negative 1.48. And we have an asymptote at y equals 0. Okay, so we have our 2 asymptotes. We've put the point at which the relative maximum occurs, the point at which the relative minimum occurs. So that's labeling all of the important values, right? So intercept, so basically these are all sort of the important values. You need to see that the domain does not contain those. We've got the equations of the asymptotes. Any symmetry? None. No symmetry, right? Okay, let's keep going. What are the non-permissible values of y equals x plus 3 over x plus 1, x minus 2? How do these non-permissible values relate to the equations of the vertical asymptotes? Okay, so the vertical asymptotes occur at the non-permissible values. So they are x equals -1. So basically we rewrite it. We write the non-permissible values as x cannot equal, and we write the asymptotes as x does equal, right? So in the equation, x cannot be equal to -1, giving us a vertical asymptote at x equals -1. Use the result from part B to predict the equations of the vertical asymptotes of each of the following rational functions. Okay, you can do that. Fill in the blanks. All right, we've had enough time. So, what are the numbers?
Negative squared. Negative squared. 0, 0, -4. -1/2.
Okay, everybody good? Next question. Number 2. Numero 2. Graph y equals 2 over x squared plus 1 on your graphing calculator and sketch graph in the table below, labeling all of the important points. Also determine the following information. Okay, so. Okay, so I'm not going to sketch this. What's the domain?
X belongs to reals.
X belongs to reals. What's the range?
Y is greater than 0, less than or equal to 2. Or, yeah, it's...
Hang on. There's a better way to write that.
0 is less or equal to 2. Yeah.
Okay, so it's between 0 and 2. What are the x-intercepts?
None.
It's a y-intercept.
2.
What's the maximum value? Relative or absolute or? Absolutely. Absolute. Minimum values? None. Equations of any asymptotes? Y equals 0. Description of any symmetry?
Reflection on the y-axis. How does the x
The y-axis, which is the line, x equals 0. All right, everything cool? I'm not going to sketch it out because we showed the sketch before. B, use the equation y equals 2 over x squared plus 1 to explain why are there no vertical asymptotes. Yes, Mo.
Since for x squared, all values must be greater than or equal to 0.
To say what? -1.
No, like if it's 0.
I'm not going to write that out.
Not 0. No.
Never 0.
Not
No undefined. Okay, can't make it undefined. All right. Next one. Graph y equals x squared minus 4 and graph calculator using the window. If you have an 84, yeah, I mean, you can still use that window, and I guess we should, right? So, what was it? Negative 4.7, 4.7 by what?
X plus 2. We don't have the window on ours. So
Oh, don't you? Oh, okay.
And what do you know?
It's okay.
All right, I don't think it matters.
It's just a straight line.
Just graph it on the
Well, yeah, actually, it's
non-friendly window. X
Get it
squared.
ourselves, right?
It looks like a
minus
straight
two.
line.
Yeah,
There.
Whoops.
Okay.
I want to put that in brackets. X squared minus 4 divided by.
I do too. I'm just eating. Oh, but it's crazy. Oh my. Not really.
Wow. Now I'm going to set negative.
My mom makes one better. Just why is yours curved?
Because you messed up.
everybody gets a straight line.
Yeah, it's true. No, Mohi's is like.
Okay. So I graphed that. I used the window in question and
Oh, whoops. It's like sag. It's like sag.
sketch the graph, labeling all of the important points. All right, so let's just graph this here as well. What was it? X squared minus 4.
Is it? No. Oh, yeah. Look at this. It's a perfectly straight line, and then for this missing things. What the hell?
0, -2.
All right, let's just start over again.
Why not just grab 0 plus?
Oh, really? All right, let's just start over again.
Yep, that is 0.7.
Divided by what? X plus 2.
Oh, that's more than 0.7. You don't need it. Once you need it, you run out of lead completely.
Okay, so there we go. So I can leave it to you to answer the questions. When there is a value of x that makes the function undefined because it makes the denominator 0, then we have either, what did we have in the first couple of examples? Asymptotes, or you have a point discontinuity, right? Point discontinuity, also known as a hole in the graph. So what's the range?
X is
No, y cannot read.
X is equal to X. Y cannot be equal to -4.
Right. So if x were -2, then y would be -4 in a more simplified version of things. X-intercepts.
2.
Y-intercept.
-2.
Maximum value.
Doesn't matter.
Minimum value.
Doesn't matter.
Equation of asymptotes.
Wait, hold on. Yeah.
Symmetry.
Well,
What?
there's a 90-degree.
It's
There's a 90 degree.
No. Remember coordinate geometry? Yeah, that.
Yeah.
what line is that?
What line is that?
-2 plus, -6. -2x plus -6.
Say what?
I don't know.
It's lost
I don't know.
minus
I don't know what I'm
negative
talking
x.
about.
Yeah, you're right.
Negative x minus 5.
I think I'm correct.
Negative x minus 6, you're right.
That's 6. See, I was right.
Woo!
Except you said plus minus. You said plus minus.
I said, okay, it was an X. I keep saying.
What else?
Oh, there's another one.
Awesome.
In a sense, well, what does the, well, we'll get there in a second. Let me just write that down for now, and then we'll get there in a second. And you'll say, oh, okay, gotcha. The graph of y equals x squared minus 4 over x plus 2 is very special, although hardly unique. Simplify the expression and explain why the graph is a straight. So why did we get a straight line anyways, right? I mean,
Yeah, because it does simplify it.
so the graph of y equals x squared minus 4 over x plus 2 is the same as the graph of y equals x minus 2, except it's not defined at the point x equals negative 2, right? So that's part C here, right? So we need to add something here, right? Which is that x cannot be equal to negative 2. So they're the same, right? This and this are the same as long as x is not equal to negative 2. So it's a simplified form of the graph. Should the graph of y equals x squared minus 4 over x plus 2 exist at negative 2? No. Why not? So negative 2 is a non-permissible value, right? Check the table in the graphing calculator. So if we go second table, and we look at negative 2, what do we get? Error. Right.
Why didn't they have just made a statement?
Because what symbol could you use on the graph you sketched above to show the graph does not exist at negative 2?
Oh my God. That's not a symbol.
So the same one that the decimals people use, right? An open circle at that point. So as we traced along that graph, we saw it go from a solid dot to an open circle, right? To say, hey, at this point, it's undefined. Yep.
How do we have symmetry along y equals x minus 2?
Because that's the straight.
Do we have symmetry along x minus 2? Like this?
This is a straight line. And you just split it down the middle of the same line.
That is a line.
You can literally.
Yes. Yes, Mohit, we do. That's why I wrote that in there earlier.
Any x.
And then said I'd explain it in a second, right? Because it's symmetrical about itself, really about that point, right? Just you-
Yes.
Yeah.
Yeah.
So, for somebody who wasn't paying attention, that's a good observation. Because you figured it out.
No, I know how you get it because it goes down like that. And then it hits the equation.
Is the graph of continuous?
How would you find that?
Yes.
Grammar.
You're doing it's this line.
Oh.
Yeah, no, so
Why not?
Because it has a whole.
point on the y.
It's got a point discontinuity.
It has a whole size of the same.
How would you find it?
So if you put negative 2 into y equals x minus 2, you get negative 4, right? And that exists on the line y equals x minus 2, but that's the value we're not allowed to put in. So then we have a point discontinuity at negative 2, negative 4. Okay? Yes, technically you need to refer to it as a point discontinuity.
That's and we're done. Can we call it a singularity?
We call it nesting down.
Can we call it whole?
No,
So let us do a little summarizing.
not maybe the line of symmetry. How did you get?
Next page has the summary.
So you draw it out. Yeah, I know, but how would you find that factor of 6?
Bios.
Pretty sure.
Let me write this.
So they give you any random number when you find the value.
So we know that polynomials functions are continuous, right? Domain of every polynomial is x belongs to the reals. Rational functions can have discontinuities. At the same time, they may not have, right? We did one that did not have a discontinuity. So rational functions, I'm going to say may have.
You can't even explain it.
Okay, and that could be a point discontinuity. And it could be an asymptote. Which can be vertical or horizontal. And there are also oblique, which are beyond the scope of this course, but they do exist. Okay, but we won't be dealing with them.
Magical curvy asymptotes. Magical curvy asymptotes.